So in this video, we're going to look at regularization for regression trees, and then we're going to be looking at bagging and boosting for classification trees. Okay, so we're going to use this Toyota Corolla case study, which is we're going to predict the price of a car. So we're predicting the price, and then here are the data inputs that we're using. Age is the age in months, km is kilometers, fuel type is petrol or diesel, HP is horsepower, metallic color indicates whether or not it's metallic color, automatic, yes or no, cc is the cylinder volume, doors is number of doors, quarterly tax is quarterly road tax in euros, and weight is weight in kilograms. Okay, so let's go ahead and read in the file. Okay, and we're now only going to use the first 1,000 rows. Okay, and that'll be because it gives you something interesting to do with the other rows. Okay, and then we're going to do our standard creating a data partition. So let's make sure that that has worked correctly. So let's click correctly down here, car df, great. And then car train df is 601, and then car holdout df is 399. Okay, and then we're going to use a regression tree here, and so it's going to be predicting the price. Okay, so we have min split, we have a CP value, we do cross-validation. Okay, and then we're going to use the lowest error plus the one standard deviation technique, which we just discussed in the previous video. Okay, so we get the cutoff, and then we go ahead and prune the tree using that best CP value, which it's just useful to know what the best CP value is. Just for fun, build up our intuition. Okay, it's 0.002. Okay. And then we plot the tree, and so here we have the results. So this number that we see at the end is the price of the car. Okay. And you see that the age seems to be the most important thing, HP seems to be important, and so forth. Okay, so that's just applying regularization to a regression tree. Same technique. Okay, now we're going to go on to ensemble methods. We're going to talk about bagging. So remember that what bagging means is that we're going to create lots of trees based on subsets of the data, typically instances, sometimes variables, and then we're going to average them together. And so here we see we're going to get 500 trees. Okay, 500 trees. So we create this random forest. Okay. And then one thing that we can do is we can plot the importance of the variables. So this is something that's very, very, very useful to understand as a data analyst. And so this tells us the mean decrease in accuracy. And so education, when you take it out, the accuracy decreases a lot. Income is also a lot. So based on this chart, education and income are the two most important. Family would be a third, and then the rest of them are pretty low. Okay? We can look at this in a different way. We can look at mean, so this is the mean decrease in accuracy over here. And so we should see something that is identical to what we see over here, right? So you see that education and income are up on the top. If we look at Gini, which is the metric that we use at the split node, we actually see that income and education are flipped, but they're still far and away the biggest, right? They're still far and away the biggest, right? So these are just two different metrics which come out slightly different for this, right? And you see other slight differences, right? So like CC average, for example, is now ahead of family, okay? So a couple of ways of looking at that. Here we look at the confusion matrix, always a useful thing to look at. Okay, we have very high accuracy here, okay? And you see what the confusion matrix numbers are, okay? And now we're going to look at boosting. So remember what boosting does is that it creates a tree, and then it creates another tree that emphasizes capturing the errors of the previous tree, by in some sense overweighting them. Okay, so we use this library called XGBoost, okay, which is a very, very famous technique. Okay, and now we're going to get a little bit more sophisticated on when we come to tuning and setting the parameters of the model. Okay, here's the cross-validation method. We're going to have 3 different cross-validation folds this time. And then we go ahead and we train the model. Okay, so we have the data being equals the training set, then the method is the XGB tree. We use tune grid and train control. So here's the model itself. And here's what the performance looks like. Okay, so performance is 97%. Okay, Okay, now we're going to compare the performance. Okay, and we're going to use the rock curve to compare the performance, which is a very, very, very powerful technique. Okay, now here we have a bunch of utility code that is going to create the model. Okay, and so what we're doing is we're using all of the three data sets that the three models that we create. So here's the best one, which is the pruned one. Here's the random forest, and here's XGB, so that we can compare all of them. And then we're going to plot it in a pretty way so that you can see it here. And what you see here is that all of the models are excellent, and they're very, very difficult to tell apart, right? Basically, you can only tell them apart in this little tiny region in the upper left-hand corner. But really, any of these models would be very, very good, and you might want to choose them based on something else, like size or interpretability, since they're all so incredibly good.